Okay, so you've memorized the reactions and now you're trying to apply them. And as you apply them, when you look at these problems, you want to identify three things. What are you adding? Where are you adding it? And how are you adding it? So you look at this recipe, for example, and you'd say, oh, because I've memorized this, I know this is, if you have a double bond or a pi bond with water and sulfuric acid, or it could also be H3O+, which is what water and sulfuric acid turn into when you add them together. Because you have that, it's acid-catalyzed hydration. And in acid-catalyzed hydration, you add hydrogen and you add OH, basically water. Where do you add them? Well, it's Markovnikov addition. So the hydrogen goes to the less substituted carbon. And you have to watch out for rearrangement. You can have carbocation rearrangement. So you have to watch out for that. And then how are you adding it? Well, if you have a chiral center, if you have it, then you'll get a racemic mixture, 50-50 mixture of the two enantiomers, because you have a carbocation intermediate that is flat, and so the nucleophile can attack with equal probability from the top or the bottom. That would give you 50% of one enantiomer and 50% of the other enantiomer. And if you don't have any chiral centers at the end, then you don't have to do anything special. Okay, so with that sort of mapped out, let's sort of apply that to this problem. So you take your carbon chain and you can pretty much just copy it, and you're going to look especially at the two carbons in that double bond. Unless you have carbocation rearrangement, those are the two atoms that the groups you're adding are going to go to. Now the first thing you're going to add is hydrogen. Where does it add? Hydrogen goes to the less substituted carbon. So this top one is primary, the bottom one is secondary, so that means the hydrogen is going to add to the top one. And the glue you're going to use to get that hydrogen there is going to be that pi bond. So the pi bond won't be there anymore. Now, we don't have to draw the mechanism, but you do have to know that at this point in the mechanism, you would have a carbocation on that secondary carbon. And will it rearrange? That's another thing we have to think about with this reaction. And you really only have to worry about rearrangement for hydrohalogenation and acid-catalyzed hydration. There are 13 reactions in this chapter. Those are the only two you have to worry about this rearrangement for. So if you notice, next door there is a more stable position for the carbocation to be at. And so you will get rearrangement, and that's where the carbocation will ultimately be. And so that's where the nucleophile is going to attack, and where you're going to have your other group, the OH. Now in this case, we don't have any chiral centers, so we don't have to do anything special. If you did have a chiral center, you would want to draw both enantiomers, so you'd want to pick two bonds, draw one of them coming out at you, one of them going away, and then redraw the molecule and switch. So the one that was coming out goes away, the one that was going away comes out. And this would be completely fine. I would be very, very happy with something like this if you drew this as an answer on an hour test. But as you continue practicing, you should really try to see it without the hydrogen drawn in. Those are meant to be seen with your mind rather than your eye and these skeletal structures. So they're implied rather than drawn in explicitly. And so that would be the product for this particular reaction. So we can go through that same thought process with any double bond, any alkene that they throw at us. You'd look at this, you'd say, okay, this is acid-catalyzed hydration, so this is what I'm adding, this is where I'm adding it, this is how I'm adding it. And you can take that double bond that they gave you, and you'll look at the two atoms in the double bond. Unless you have carbocation rearrangement, that's where the two groups you're adding are going to go. And in this case, this carbon on the left is tertiary, the carbon on the right is secondary. So this is Markovnikov addition, so the hydrogen goes to the less substituted carbon. That's going to be that secondary one. And you're going to use the pi electrons to stick it there, so you won't have those anymore. And although you don't have to draw the mechanism, you should know at this point you'll have a carbocation on the other carbon, and it can rearrange. Will it rearrange? Well, we have to check. In this molecule, next door, we only have less substituted positions. And so a secondary to the left, secondary to the right, and primary above. And so those are all places where the carbocation would be less stable. It's on a tertiary position, which is more stable. So it's not going to rearrange. Just because you can have rearrangement doesn't mean it will happen every time. So in this case, it's already on the most stable position. You won't have rearrangement, and so that's where that carbocation is. That's where the nucleophile is going to attack, and that's ultimately where you're going to add your second group, which is the OH. Now in this case, again, we don't have a chiral center, so we don't have to do anything special. But if you did, you would pick that two bonds on that chiral center, and you would have one bond coming out at you, one going away, and then you'd redraw the molecule, so you'd have it drawn 2 times. And in the redrawn molecule, you'd have the one, you'd switch. The bond that was coming out would go away, the bond that was going away would come out, so you'd have the 2 enantiomers drawn. And I would be more than happy with this as an answer on our tests, but as time goes by and you practice, you really should be able to see this, you should really be able to see the product without the hydrogen drawn in explicitly. So this would be the synthesis product, the product of this one-step synthesis of this acid-catalyzed hydration on this alkene.